That's easier. Okay, here goes nothing.
Got it. Yeah, it's my Zoom. Oh, there's Nick. Okay. Is Kezhou on yet?
Yeah, just joining now, I think.
Okay.
Yeah, I'm here.
Hi.
Hi,
Shia.
Jenna.
Hi, Shia.
Intro.
Oh,
It's
there's
true.
Kezhou.
Hello.
Hey.
Hi. Kezhou, would you like to just test sharing your screen just to make sure we've got that from
Sure. You,
everyone?
you guys can hear me, right?
I can hear you just great.
Mhm.
Okay. Let me see. Can you see the screen?
Excellent. Yes.
Mhm.
Should I just keep this here or should I just exit other people to try
yeah.
it?
Exit because I'll need to share the sort of intro slides in a sec.
Sure.
We're really getting all the different. You can tell which time zone people are in by the darkness of their. Like, so Jonah's clearly in Europe now. It's a dark room.
Yep.
Very dark.
Kezhou's on the East Coast,
very
right?
dark
So
room.
yeah.
Yeah, the only other light in here, it just has this terrible glare that's like right in the background. And so this is the like, yeah, I have to figure this out, but anyway, let me put up the intro slides. Does this look good? Can you see it?
Mhm.
Okay. And now I can't even see what time it is. So Andrew, maybe just let me know when it seems like, or Shia, someone let me know when it seems like it's the right time to kick off.
Yeah. Christy is gonna be a couple of minutes late, he said. So
He'll be a few minutes late. Andrew and Shia, how are we looking?
For time?
Or just should we start or?
I'd maybe give it another like minute or two, I think, because it's only 12:01.
Okay.
Jonah, you want to start now, or the speakers are here?
Okay, let's do it. Hi, everyone. Welcome to the 29th ECS and Cloud Feedback Virtual Symposium. Thank you guys so much for joining us today, this evening or morning or afternoon, wherever, whatever it might be, wherever you are. We have a really great program today. We have 3 speakers, each with 12-minute talks. There'll be a little bit of time for some questions after each talk. So if you have any questions, please just type them into the chat at any time, or you can raise your hand and we'll unmute you and you can ask your question directly to the speaker. If you have ideas for talks for the future, we're looking for speakers for next year. Please get in touch with any of us on the executive committee, and you can find our contact information and all sorts of other information, including videos of past talks, our mailing list, sign up, and much more at our website here. And with that, we're going to go to our first speaker. So I'll stop sharing. And our first speaker today is Kezhou Liu. She's a graduate student at Georgia Tech studying with Professor Kezhou, and she'll be talking about mechanisms of fast Walker circulation responses to CO2 forcing. So take it away, Kezhou.
Yeah. You guys can hear me all right?
Yes.
Okay, thank you. Okay, thank you for inviting me to give a talk. Today I'm going to share a work that is done a couple years ago about the mechanisms of fast Walker circulation responses to the CO2 forcing. This work is collaborated with my advisor He and Dr. Fosso and also Maria from Colorado State University. And then I also put a DOI number here if you wanted to know more information. Please you can go in and read the paper. And if you have any questions, feel free to stop me and ask questions. Okay, so to start with, what is the Walker circulation? I mean, we all know like the Walker circulation is a zonally overturning flow that is confined within the tropics. And it is characterized by the deep convection over the warm pool in the Pacific and a trade wind blowing from the east to west in the low level, and as well as a upwell in the cold town. So a lot of studies are wondering, as the global CO2 increases, are we expecting a strengthening or a weakening of the Walker circulation? So if we have a weakening of the Walker circulation, and then we will expecting the deep convection moves eastward and also weakens, and then we will also expecting a weakening of the trade winds in the low level, as well as less upwell in the cold town region. On the other hand, if we will have a strengthening of Walker circulation, then we will have more deep convections in the warm pool, a strengthening and westward expansion of the Walker circulation, as well as a strengthening of trade winds and upwelling. So the climate communities have projected a long-term weakening of the Walker circulation in response to the long-term increase of CO2 concentrations. For example, here is a very classic Held and Stoughton paper in 2006. So on the left plot, they look at the percentage changes of column-integrated water vapor plotted against the global mean changes of surface temperature. As you can see, the relationships follows the Clausius-Clapeyron relationship, which is 7.5% per Kelvin. However, if you look at the precipitation changes against the global mean warming, then you see this rate of changes is about like 2% per Kelvin, which is much lower than the Clausius-Clapeyron relationships. And in this paper, they attribute these discrepancies as the weakening of the Walker circulation response. However, if we look at the observational records, and we actually see a strengthening of the Walker circulation. For instance, here is a plot of a SST trends as well as the low-level wind trends that is taken from the observational data set from the last couple of decades. As you can see, here is clearly a strengthening of the trade winds as well as a cooling trends. And then some of the scientists attribute this to the internal variability. For example, here on the right plot shows a correlation of the Pacific Walker circulation and the interdecadal Pacific oscillations. And then it seems like they have a correlation here. However, some other scientists think that the climate models are wrong in representing the tropical SST. For example, in the SIGAR 2019 paper, they look at the Nino 3.5 SST trends from both observational dataset and CIMIP 5 CSM large ensembles. For example, here, these like blue little dots are the CIMIP models from all different 85 models. And then the black ones are the model ensembles taken from the 40 large ensemble in CSM. However, you can see like these are large ensemble and multimodal ensembles supposed to capture the internal variability relatively well, but you still see the observational records falls far out of this range. So this work is wondering, so are we missing some fundamental understandings of the model simulated water circulation? So before I delve into the actual content, here I would like to introduce the different mechanisms that drive the changes in the water circulation at different time scales. So here we can roughly separate these mechanisms into a slow component and a fast component. And the slow component are dominated by the oceanic elements, while the fast responses are usually more tightly to the atmosphere. So for example, if you give perturbations, say like a broad 4 times CO2 forcing to the atmosphere, so you will first of all has a weakening of the radiative cooling. And these direct radiative forcing will causes the land surface to change, and you will have an initial lensithermal contrast. And these will also cause some spatial pattern of SST changes. All of these will communicate to the oceans. And after like several centuries or even up to 1,000 years, and then the ocean will slowly warm up. And then the long-term SST warming is going to drive the atmospheric changes. And in this time, you will see like the paradigms like the warmer get wetter and wetter get wetter. So the long-term changes is more robust and it's more gray among models. However, the fast changes is largely rarely studied, and then it's not reaches a consensus. So here, how do we separate the fast and the slow components? So there are a lot of works use a fixed SST experiment to get rid of the SST warming. And there's some other ways. For example, if you take a fully coupled GCM and you abrupt forcing to the GCM, and then you can separate the fast and slow components based on the time scales. For instance, here, I can take the changes within the first 5 years as a broad forcing, as a fast response period, because in this time period, the ocean hasn't got enough time to warm up. And then we can take the slow response as like years after 100, 120 years when the mixed layer reaches a quasi-equilibrium. Okay, so let's look at some fast changes from the models. So here I have shown some randomly sampled CIMIP 5 models, and I have plotted their SST changes in the average over the first 2 years of the abrupt 4 times CO2, as well as the low-level wind changes. So as you can see here, some of the models show like a central coolings in the SST and also a strengthening of the trade winds, which indicates a strengthening of the water circulation. On the other hand, there are some other models do not have the similar features. They just seem to have a weakening of the trade winds, which indicates a weakening of the water circulation. So it is very intriguing what causes this intermodal discrepancies in fast water circulation changes. And on the other hand, because most of the previous work used the fixed SST experiment to study the fast component changes of the circulation, so the air-sea coupling in the fast response period is actually rarely studied. And so this work will focus on answering these two questions. So our methods are listed as below. So first of all, we look at the 27 CIMIP 5 models from the abrupt 4 times CO2 scenarios. And I separate these models into a cold group model, CG model, and a warm group models, which is WG models. And I will explain how I separate them in a second. And then also to study the fast response, we use like a broad 4 times CO2 large ensemble to eliminate the internal variability. So these experiments are designed as below. So first of all, we have a very long pre-industrial control run. And at different time periods, we branch off a broad 4 times CO2 ensemble. And then we run 120 ensembles. And then we take the ensemble mean of each month for an individual ensembles and then average them together and get an ensemble mean of the response at a corresponding time period. Okay, so here are some notations used in this presentation. So the changes are represented by this little triangle sign. That means the abrupt full-time CO2 run minus the pre-industrial control. And the total response is defined as the changes average over the last 30 years of simulations. And the fast response is defined as any changes within the first 2 years. And the slow response is the total response minus the fast response. So here, if we look at the SST changes within the Nino 3.4 regions, and we calculate them for each individual models, and then we rank them. So here you can see, like, there are about half of the models has a value below the multi-ensemble mean, and the other half is above the multi-ensemble mean. So here we group the lower half of the models as semi-5 cold group, and the upper half of the models as semi-5 warm group. And then you can see the CCSM4, which is very similar to the CSM1 in the cold group models. And CSM1 itself is also part of the cold group models. Okay, so now let's look at the fast response of these different model groups. So immediately after we abrupt full-time CO2 forcing, here on the left column, I show different model group responses in the first month after the abrupt full-time CO2. As you can see, across all 3 model groups, you have an initial lengthy thermal contrast, and these thermal contrasts will induce a landward winds in all 3 groups of models. However, as time fast forward, if we now look at the month 7 to month 9 responses, then we can see in some of the models, so the CSM1 large ensemble models, as well as the cold group models, you see a central Pacific cooling, as well as a strong anomalous easterlies. And however, in the warm group models, you see an Eastern Pacific warming, and there's no anomalous easterlies observed here. So that is being said, in the cold group models, as well as CSM1 large ensemble, we see a fast strengthening of the Walker circulations. However, we do not see the same strengthening of Walker circulation in the warm group models. And now we wanted to know what causes these intermodal discrepancies in the fast Walker circulation changes. So the first question we wanted to ask is this discrepancy robust or does not contaminated by the internal variability? So here we use the Monte Carlo method to quantify the internal variability. And this is the error bar shown on the left plots. So on the left plots, I calculated the changes in the Walker circulation strength as the color bars. And the error bars are the intervariability ranges that is quantified by the Monte Carlo method. If the color bars surpass the error bars, that means the changes are robust. So as you can see, within the first 2 years, the cold group models and CSM1 large ensembles has a very significant robust response. And then the warm group also has a robust response. So we can say, yes, this intermodal discrepancy is not because of internal variability. And the second question is, does the parent pre-industrial simulations ENSO state matters? So saying that, I was trying to see maybe when I abrupt the full-time CO2, for some models, their pre-industrial experiments is just going through a El Nino or La Nina state. So maybe the time I abrupt the full-time CO2 will influence my results. So here I look at the pre-industrial control ENSO state when I abrupt full-time CO2. So here the E means that the El Nino is happening when I quadruple in the CO2, and the L means when La Nina is happening when I quadruple CO2. So as you can see, we do not really see a significant trends or differences between 2 model groups. There are some models that are going through a El Nino, there are some going through a La Nina, but maybe that's not what is happening here. And then the third question is, maybe the cold group models just have a larger lengthy thermal contrast that is going to induce more easterlies in the Pacific warm pool. So here we plotted the lengthy thermal contrast index and against the surface wind average over the first 3 months. So if you go up on the vertical axis, that's westerlies, and then if you go down, then it's the easterlies. And then each different triangle, each different star size and a circle means the different models. So as you can see, we don't see a very significant or robust relationships between the lensing thermal contrast and different model groups. So the answer to this question is no. And then so the last hypothesis is maybe the model just simulate different ERC coupling strength. So I quantify different models, ERC interaction strength in their pre-industrial runs. So I use the SST budget equations and did some modifications, but eventually I came up with a diagnostic equation to quantify the feedback within different models. So the total feedback index here has a component of convective cloud feedback and then wind evaporation SST feedback. And then both of them are summed as the thermodynamic feedback. And then there's also a component to measure the Bjerknes feedback, and a third component to measure the donor advection feedback. So a higher total feedback index indicated more sensitive ERC interaction within each model's pre-industrial run. And now let's look at how different models does. So here I show like the model group mean of 3 different feedback index. So as you can see, the co-group models have a relative higher Bjerknes feedback index and a zonal feedback index, which led to a higher total feedback index numbers. And compared to the co-group models, the warm group models doesn't have as strong feedback index as the co-group models. So with that being said, in the co-group models, because their parent runs has a more sensitive ERC coupling in the tropics, when you give a little bit of perturbation in the winds, that will trigger a positive Bjerknes feedback loop, which will eventually lead to a strengthening of Walker circulation and then the cooling of the central SST. However, in the warm group models, because the perturbation in the winds is not enough for them to trigger such a positive feedback loop, so that you don't see a strengthening of the Walker circulation in a fast response. Okay, so now we know that's possibly be the answer of the intermodal discrepancies in a fast response period. Okay, so now let's look at how the fast transits to slow response period. Here I plotted a time evolution of the equatorial Pacific subsurface ocean that I averaged over the 2002 north. So here the left column is the CSM1 large ensemble from the first year to the year 4 and year 5 and so on. And the middle one is the cold group, and then the right one is the warm group. As you can see, in the cold group and then the CSM1 large ensemble, you see like a strong anomalous easterlies piling up warm waters to the west coast of the Pacific. And then as the background gets warms, these like easterlies started to weaken, and those like warm bob of waters will start to propagating towards the east as the downwelling Kelvin waves. And the Kelvin wave response will eventually wash out the cold anomalies you see in the first couple of years. And on the other hand, the warm group, you just don't see such a non-monotonic responses. It just warm throughout the fast to the slow response period. And the slow response period, you can see 3 different models. They all have a central Pacific warming, awakening of the trade winds, and also overall background tropical warming. So to summarize, there is a time chart plot of the fast response to the slow response period. So when you first absorb full-time CO2s, that the landward, the lensing thermal contrast will induce landward wind anomalies in both model groups. But for the model that has a more sensitive ERC coupling, you will tend to trigger Bjerknes feedback, then will lead to a strengthening of the fast Walker circulation changes. But for the warm group, you don't see such a changes. And then as the overall background started to warm, both cold group models and warm group models, they all start to warm together and eventually leading to a slow weakening of the Walker circulation response. Yeah, and then this is my talk. Thank you for your attention.
Thank you, Kezhou. That was a really great talk. And you've already prompted some questions in the chat, so I'm just going to read them out. So first of all, question from Paolo, which says, is the ERC coupling feedback estimated from the PI control runs? And are the values averaged over specific regions?
So Yeah, thank you for the question. So yes, the heuristic coupling is estimated from each model's long control run. And then the different well, let me go back to the sorry. Sorry.
It's okay. Zoom is
I was trying to pull out that slides with response. Okay. Yes. So here, this is like a different index. So like I calculate them along the entire equatorial Pacific from 5 south to 5 north. But then these index, they are from both atmosphere and also oceans. So for instance, if you look at Bjelknes feedbacks, I use the entire zonal wind in the atmosphere and also the entire zonal mean of SST. But here there's also a variable as the thermocline depths. So here I also only look at the thermocline shoreline in the Eastern Pacific cold-town regions. And then this is the subsurface ocean temperatures. I believe I also only look at the cold-town regions. Yeah. Oh, there's a detailed derivations in the paper, then you can check it. Yeah.
cool. And then I think we have time for one more question from Zhihong, which asks, I think related to this slide as well, which is how good is the correlation between ASC coupling and the ENSO response across models? Can we use this to develop an emergent constraint?
That's a really good question. I actually tried to do it. But yeah, so if you think of it, so the ENSO response is basically, you can think of it as like a, ASC coupling and then some stochastic wind forcing, right? So supposedly the models has like a more sensitive ASC coupling might have a more frequent ENSO or La Nina, like just ENSO frequencies. So I did tested this with different multi-ensemble, large ensembles with different like modeling standards. And seems like the co-group models, such like MPI and then CAN ESM5, they seems to have like a more frequent El Nino La Nina happening within their large ensembles compared to some other warm group like MIRO5. Yeah, but I didn't succeed in developing an emergent constraint for it because I think the stochastic forcing part is very complicated to quantify. So yeah, I don't know how to do that. If you know, do let me know.
That sounds really interesting though, and a great technique for diagnosing all this stuff. There are more questions in the chat, so maybe you can answer those during the next talk.
Sure.
Yeah. But next up we have Marysa. Actually, I'm not meant to be introducing. John is meant to be introducing. Sorry.
That's okay. Our next speaker is Marysa Lague, assistant professor at the University of Utah. And yeah, she'll be talking about continental configuration and water vapor greenhouse effects. So take it away, Marysa.
Great. I'm very happy to be here. So I'm going to be talking, like they just said, about half land and half water planets and how continental configuration modifies large-scale climate. So we typically think about changes in evapotranspiration, in particular reductions in evapotranspiration from the land surface, as having a warming effect on the land surface. So just like sweat cools people on hot days, evapotranspiration from land, so that's just combination of evaporation like from a puddle or from the canopy, and transpiration, which you can think of as water that's actually going through a plant and out to the atmosphere, has a cooling effect on the land surface. So if you turn those down, that ought to have a warming impact on surface climate. And we can really clearly see this impact of ET on surface temperatures using infrared cameras over vegetated land surfaces. So the top panel here is showing you a pinyon juniper woodland in California, where the sort of tan colors are bare soil. So it's pretty dry. The soil has dried out in that top layer. And then the green areas are showing you where there's trees. The bottom image is the exact same scene, but it's taken with an infrared camera, and the colors are showing you the temperature of the surface. So you can see that the vegetated surfaces are much, much cooler than the bare soil because they're able to transpire to keep themselves nice and cool. So Main point here is just ET from the land helps to keep temperatures cool, which means that if you make it harder to cool the land with evapotranspiration, you would expect that to have a warming effect. And this isn't like a surprise or anything. This is something we've understood or thought we understood for a very long time. So this is a pretty seminal paper by Shukla and Mintz in 1982. And the top panel is showing you surface temperatures from GCM in July, where the soil was forced to be wet. And the temperatures are fairly cool. You can see that from the sort of wide spacing of these temperature contours. The bottom panel is from a dry soil simulation, also for July, and you can see that the land surface temperatures are much, much hotter when you don't allow the land to evaporatively cool itself. We also get the same result using sort of modern Earth system models. The figures on the right are showing you the difference in temperature, surface temperature, between a simulation where we force the land to look like a desert, so we have no soil moisture, no evaporative cooling of the land surface at all, compared to a land surface where we artificially allow the land to have as much water as it wants to evaporatively cool. So this is sort of a desert land you can think of compared to a swampland. And these also show warming over the land surface. There's two panels here because the top one is done with CESM, which has cloud feedbacks. So not only are you getting warming because you reduce evaporative cooling of the land surface, but you also get a big reduction in low cloud cover over the land surface that leads to extra shortwave warming of the land. So you get lots and lots of warming there. The bottom panel is done with an idealized global circulation model called ISCA that doesn't have any cloud feedbacks. So then we're getting not quite as dramatic warming, but we're still getting that warming due to the reduction in evaporative cooling, even though we don't have that cloud feedback there. So really you can think of this as all being driven by the surface energy budget. Unlike the ocean, land has to get rid of all of the energy that comes in at any given point. So if you've got shortwave and longwave radiation coming into the land surface, it has to shed that energy either by reflecting it, emitting it as temperature, or letting it out as sensible and latent heat. So if you, for some reason, turn down your latent heat flux, for instance, by chopping down a forest and replacing it with a parking lot, or by plant responses to increasing CO2. If you turn down that latent heat flux term, that's going to lead to increases in surface temperatures and potentially extra large increases in surface temperatures if you get atmospheric feedbacks. But the question I wanted to focus on today is how much of what we think we know and understand about the climate system, and in this case about how land surface temperatures are impacted by evapotranspiration, is actually just a novel feature of our current modern Earth system. So if we think about our modern Earth, it isn't actually very water limited in terms of the whole planet. There's lots of ocean at every latitude, and most of the planet is actually covered with ocean. There's about 30% land. Come on, slides, there we go. But we can also ask the question, what about other continental configurations? So reducing terrestrial evaporation doesn't seem to have huge impacts on global water vapor concentrations in our modern continental configuration. But paleogeologists have put together these time series of past continental configurations for up to 1 billion years. This video is just showing you, I think, the last 400 or 500 million. And you can see that there are times in Earth's history where the land has been clumped into big supercontinents or broken apart into many smaller continents like it is today, when all the land has been stuffed into one hemisphere or when it's been sort of stretched from pole to pole. And we can ask how the distribution of land over the surface of a planet influences how land is actually interacting with the climate system. And to do this, we're going to do some pretty idealized simulations where we're going to start off focusing on the fact that there's more land in the northern hemisphere than the southern hemisphere in the present day. So what if we just sort of make a really idealized version of that? And we're going to look at 3 cases here. So there's this 2-patch land scenario. You can think of this as 2 big continents, for instance, the Americas and Eurasia, separated by an Atlantic and a Pacific. And then what happens if we sort of shove those continents together into just one big continent, but they have the same total amount of land? And then we can contrast that to the extreme scenario of more land in the northern hemisphere, which is just covering your entire northern hemisphere with a continent and your entire southern hemisphere with an ocean. And then we can run the same kinds of experiments that I was showing you in the introduction, where we turn off land evaporation and see what it does to surface temperatures. And we're doing this in that ISCA model. So the key things here are that the land is different than the ocean. It's brighter, it has a higher albedo, it has a smaller heat capacity, and it has a limited capacity to hold water. So it has a bucket model for hydrology. So it's capturing sort of the basic differences between land and ocean. The atmospheric model, it can simulate precipitation. It has the RRTM radiation model, so it's got radiatively interactive water vapor. The key thing here is that you can think of the clouds as being invisible, which obviously isn't realistic, but clouds are also a major source of uncertainty. So at least we know how they're wrong in this scenario. They just are invisible, and we don't have to worry about what their feedbacks are. So then we can ask, for these idealized continental configurations, what happens if we suppress land evaporation? And that's what I'm showing you here. So this is the difference of two simulations, one where it's hard to evaporate. We've made the bucket really tiny compared to just a regular land surface model. And what we see is that we get warming over land. The continents here are just shown by these outlines, and you can see most of the land is red. Land is generally warming on average by about 1 Kelvin in the suppressed evaporation scenario, where the exception is sort of in these desert areas where they don't have any water in the first place. So the dry land areas, they aren't getting any warmer from suppressed latent cooling just because they don't have any latent cooling to begin with. So far, this is pretty consistent with everything we've thought about so far in the more realistic scenario of our modern Earth. We can do the same kind of experiment with this northwest land situation, shove the two continents together. And again, we get warming over the land. It's not quite as big, but it's still generally red over the continent. We can then ask what happens if we just have one really big northern hemisphere continent. And something completely different happens. So the first time I plotted this, I thought I just screwed up and plotted it backwards, but this is actually plotted the right direction. And you do actually get a huge amount of cooling when you suppress evaporation over this Northland scenario. And what's happening here is that the lack of any oceanic water vapor source in the Northern Hemisphere means that any warming you get from reducing evaporative cooling of the land surface is way smaller than the massive cooling effect you get from just reducing atmospheric water vapor over the entire Northern Hemisphere. And that cooling from the lack of atmospheric water vapor, which is a really strong greenhouse gas, ends up dominating your surface warming. So in this case, this Northland scenario, we have a continental configuration where the change in land evaporation actually has a huge control on atmospheric water vapor concentrations. And water vapor is a really important greenhouse gas in our modern continental configuration too. It's about half of the modern greenhouse effect. So if you have a planet that has relatively low amounts of water vapor, you would expect that to be cooler compared to a planet with lots of water vapor. So what we can think of is that if you're reducing land evaporation, you can think of which effect wins in terms of cooling from a weaker greenhouse effect versus warming from less evaporation. And this is sort of a battle between the greenhouse effect and the surface energy budget. And what we see is that you can sort of put different continental configurations scattered along this graph, where initially, if you reduce land evaporation, you get warming. And this in particular happens if you don't have very much land in total, or if your continents are broken apart by lots of oceans. Whereas if you have large enough continents or enough total land area, then reducing land evaporation ends up reducing atmospheric water vapor to the point that you actually cool your whole planet. So there's plenty of ocean in the modern continental configuration, so we're very much towards the left-hand side of this plot in our current climate. So the take-home point here is just that land can impact water vapor greenhouse effect. Cool. But what we can then focus on is how the amount of land versus the distribution of land sort of controls where you are on this sort of schematic. So to do that, we can ask what happens if we have some really just out there wild continental configurations. And in particular, if we compare these to sort of that Northland situation where we had half land and half water planets, we can ask, what do other half land, half water planets look like? So Northland we already looked at, it's right here, but tropics land is also half land, half water, big continent in the tropics, oceans on the poles. We can compare that to a big tropical ocean with land on the poles, or what if we just had sort of a big continent going from pole to pole, sort of in the eastern hemisphere with a big ocean in the western hemisphere. And then we can compare those idealized scenarios to sort of an aquaplanet, a planet that's all land, or a sort of idealized representation of our modern Earth. And in particular for today, I'm going to compare the sort of base state climates of the aquaplanet, the tropical land planet, and the polar land planet. And again, these are done with ISCA, so the land is brighter than the ocean, it has a smaller heat capacity, and it has a limited capacity to store water. And we can ask, which planet do you think is going to be the warmest, and which one do you think is going to be the wettest, just in terms of water vapor? I don't know what your intuition on this was, but mine was that, you know, the aquaplanet, it's really dark, it has a low albedo everywhere, it's got plenty of water everywhere, so it should be pretty warm and it should be pretty wet. maybe tropics land will be pretty hot because it's got this huge tropical desert, lots of sun, deserts in the tropics tend to be hot. That is not what happened at all. So if we plot global mean water vapor on the x-axis and global mean temperature on the y-axis, and then just scatter all of these planets on this space, what we see is that the ones we really care about here are the orange triangle, that's our tropics land, the blue circle, our aquaplanet, and the gray triangle, that's polar land. Tropics land is actually really cold and really dry. It's almost the coldest, driest planet we have. The aquaplanet is pretty hot and wet, but polar land is even hotter and wetter than the aquaplanet, which is kind of weird. So what's going on here is actually all to do with water vapor, which may not be a surprise given that I sort of led into this from the water vapor point of view. So tropics land is really cold because it has this massive continent going all the way from 30 south to 30 north, which is basically blocking all moisture transport of your trade winds to bring moisture onto the continent. So the water just evaporates off the land, can't really get replenished. So you end up with this really dry atmosphere, which ends up being a really cold planet. The aquaplanet looks sort of like we would expect an aquaplanet to look, lots of evaporation in the tropics where you've got the most energy coming in, which is also what this tropical ocean scenario looks like with the polar land. What's cool about the polar land, though, is that it's actually, sorry, too many slides. It's actually got even more water vapor going on in the high latitudes than the aquaplanet does. And what's going on here and what's resulting in these high latitude land areas having more water is actually all to do with the heat capacity of land and the seasonal cycle. So what's going on is that in the aquaplanet, it can take up lots of energy during high latitude summer, and it doesn't actually have to heat up that much. Whereas the polar land, it doesn't have a big heat capacity, so it's got actually quite a bit of water on the land. So it gets these really large increases in temperature and increases in terrestrial evaporation during local summer. More evaporation means more water vapor, which actually influences the local greenhouse effect during summer, which leads to even more surface warming and even more evaporation. So you've got this local feedback of water vapor that's happening over your high latitude land in the polar land case that you don't have in the aquaplanet, that allows you to have an even warmer and wetter planet when you have land over the poles than if you just have an aquaplanet. So the point here is just that continental distribution, it can actually have a really big control on the base state of a planet's climate. And it does this largely through modulating the amount of water vapor in the atmosphere. And then I just threw this last slide in here for fun since it's an ECS symposium. We also ran all of these at 2 times CO2. We actually ran them also at like 4 times and up to 16 times CO2. But all of these different planets, they have really different equilibrium climate sensitivities. So the aquaplanet here is in blue. The tropics land has a much smaller ECS in orange. The polar land, which sometimes we call Kapland, in green. And there's a pretty decent spread in ECS across these continental configurations. So yeah, that's just kind of a fun fact, but the main point here is that land matters for climate in interesting ways, in particular through doing weird stuff to water. Yeah.
Thank you, Marysa. That was fantastic. I think we already have a question from Jihong, if I could find that. Yeah, so it says, very impressive work. It would be interesting to repeat these experiments with the GCM with clouds, because the cloud radiative effects can partially compensate the water vapor effect. I guess
Yes.
I guess I had a comment following on from that. Like, I know ISCA now has like a simple cloud scheme. I don't know.
It does. You have to email someone at the Met office to get it, and I've been too chicken. So has
Oh.
anyone emailed them and will they give it to you? It's not publicly available. So that's one thing. I just need to email the person at the Met office and get over being chicken. And then the other one is that, so the reason I did these with ISCA in the first place, as opposed to CESM, which has clouds, is that it's really easy to move land in ISCA. That said, CESM has a new coupler where it's much easier to move land than it used to be. So it's now fairly straightforward to repeat these in CESM. When I first ran them, it was like a lot of work to make every new continental configuration, but now it's not. So stay tuned, because I also want to know what they look like with clouds, especially mesh land, like alternate one. I bet it's very cloudy.
Yeah. We have some questions in the chat. We had Nader has his hand up as well. So maybe Nader, you can unmute yourself and ask.
All right. Hi, Marysa. This is Nader Jeevanji from GFDL. Great talk and mind-expanding experiments. I was interested in your explanation of polar land. You talked about the seasonal cycle having an outsized impact, and you talked about summer. But of course, over land in the wintertime, you can also get strong wintertime inversions and strong cooling. And of course, we see that in land masses in the Northern Hemisphere, for instance, Siberia, where you get extremes in both summertime and wintertime. So how come that doesn't offset or cancel out what's happening in summer?
Yeah, so in winter, you actually get colder land over polar land, or colder surface over polar land than you do over the aquaplanet, which again, you might expect from the big difference in heat capacity. But the difference in temperatures and the difference in total surface fluxes that you get in wintertime, I realize this is a lot that I just put up on the screen to take in like 10 seconds. But those differences are just much smaller than the changes in temperatures and the energy budget that we see in the summertime. And I think that's all coming from that sort of water vapor feedback. So it's more than just the heat capacity. You need that extra water vapor feedback, and we only see that in summertime.
I see. And does that sort of difference in the seasonality, is that similar to what we see on Earth? Sounds like it might be a little bit different.
I don't know. I think it could be similar because there's, at least in the Arctic, there's plenty of pretty soggy land in the summertime, or it could be similar to what we're going to see as more and more of the sort of permafrost thaws. So it could be sort of interesting to compare what we see in the Arctic versus the Antarctic, which is much more frozen in our real Earth. That would be neat. And I don't think we know how big that is in our modern climate. Like, how big is our water vapor feedbacks coming from land ET in the Arctic? If you know that number, please tell me, because I don't know that number.
All right, sounds good. Thank you.
Great. You've sparked more discussion in the chat as well. So I think we'll move on to Christy now. But yeah, if you want to answer stuff in the chat, that'll be great. Thanks again, Marysa.
Hello, everybody. Can people hear me?
Yes. Go ahead, Christy.
A man who needs no
Okay.
introduction.
That's right.
Okay. Are you seeing the presentation?
Yes.
Right. Okay, you're not seeing the presenter screen. Awesome. Okay, so hi, everybody. Thanks for inviting me back as I have made the promotion from organizer to citizen. And today I'm going to talk to you about whether we can learn spatial radiative feedbacks from a short record. This is work funded by Department of Energy under the Regional and Global Model Analysis. And from the climate dynamics and data science, this is definitely under the data science part of what I work on. So let's get right into it since time is short. I'm going to give you a bit of background on climate sensitivity and pattern effect. I'm going to go fairly fast through it given the audience. Then I'm going to talk about some linear regression approaches. Then I'm going to talk about how and why they work, which took me a while to understand. And then I'm going to talk about hierarchical Bayes. And actually, I started with the Bayesian part and then wanted to do some silly linear regression and was surprised by the results. So this is not the order in which things happen, but I think this is the order in which it makes sense to present them. So background, we start with Earth's energy budget. We look at the top of the atmosphere net imbalance, and that is decomposed into a radiative forcing F and a radiative response, which is a function of temperature change. Hopefully everybody's familiar with this equation in this audience. And the usual approach is to decompose, this into to assume that the radiative response is actually just a function of global temperature anomalies linked by a global feedback term lambda, which can be thought of as a Taylor expansion of the radiative response in global temperature. So this lambda is how global radiation depends on global temperature. Under this assumption, you can then take the system to equilibrium, where by definition the net imbalance is zero, and then radiative forcing is balanced by radiative response, and you can infer climate sensitivity as being forcing divided by feedback. If the feedback is very negative, this term is going to be very large, and the Earth doesn't have to work too hard to close the energy budget. So you get low climate sensitivities, the feedback is more positive or less negative, then the Earth has to warm more before it can close the energy budget. Right, so this is the traditional view of Earth's energy budget and climate sensitivity. And what we've recently understood is the pattern effect, which is that radiation really depends on the full pattern of warming. So in the linear view, you can think of this as instead of Taylor expanding radiation as a function of global temperature, you Taylor expand it as a function of regional temperature anomaly, where T_x means that you're now looking at temperature at all locations on the Earth X. So speaking of expanding, we can expand this equation a little bit, and we can look at the different terms. So radiation is a function of the sensitivity of global radiation to regional temperature. This is what is usually been estimated using Green's function analysis in GCMs, where you put a delta function like perturbation and you look at the global radiative response to temperature perturbations in different regions, right? Hopefully everybody has, by this point in this audience, has seen these Green's functions, and this is the CAM5 direct estimate of a Green's function. Now, if we want to go to a feedback, all we have to do is we have to divide this global radiation by global temperature to get a feedback. And what this means is that the feedback in this linear decomposition is proportional to this radiative sensitivity times the warming pattern. And what the pattern effect means that if we look at two different patterns, for example, on the top, the recent observed pattern of warming with more warming in the West Pacific and cooling in the East Pacific and Southern Ocean, this should actuate more negative feedbacks. We have positive sensitivity times negative warming in the East Pacific, so that's going to be strong radiative damping, and we have more warming in regions of very strong negative sensitivity. So both of those are going to lead to more negative damping. Whereas if we look at the more uniform long-term pattern, we expect a more muted response. So if we were to infer climate sensitivity from these two experiments, which is, take the feedback, divide forcing by feedback, and infer climate sensitivity, we would find a much lower climate sensitivity from models run with the prescribed historical SST versus the long-term pattern given by climate models. And this difference is known as the pattern effect. And the problem with it is we have a good understanding at this point about the dynamics, what it does in models, a good idea of the physics. We have very poor, essentially no observational constraints. So there's sort of two problems, I would say, big in the field right now. One is what causes this pattern. The other one is how do we place some observational constraints on this radiative sensitivity? And that's really what I'm going to talk about, is focusing on trying to understand the sensitivity of global radiation to regional temperature. This is what I would call regional feedbacks. So you can think of this as a linear problem, a linear model where radiation as a function of time is essentially a linear model, linear regression, where the regression coefficients beta are the sensitivities of global radiation to regional temperature. And we would like to see whether we can place observational constraints on them. I'm not actually going to place observational constraints today. I'm just building a framework for it. So that's what we want. What is the problem with that? Well, for one thing, if you want to do this via least squares, you need to have fewer regressors, fewer betas than you have observations. We know, at least in direct model estimates, we need about 150 degrees of freedom to estimate this. We only have 20 years of satellite data in the series record, so it's a terribly under-constrained problem. That doesn't mean that it hasn't, people haven't done some interesting work on this, so I'm going to talk a little bit about what have been some linear regression approaches to this. And again, the problem is one of estimating this linear sensitivity of global radiation onto regional temperatures. Historically, if you want to do this with least squares, then you need to observe this OLS condition. So Kezhou did it in 2017 using 50 years of series record. I'm not entirely sure what Chen did in this paper, but I think what he did was he actually did a linear regression at every point. So that's going to double count places where temperature is correlated. But it gives you something reasonable. Jonah and Maria did this, the multilinear regression in a paper in 2020. And to observe the OLS condition, they needed to block this into 15 degree by 15 degree and use 1,000 years of simulation to get something that's fairly low resolution and blocky. And more recently, Sarah Kang and Paolo Ceppi used ridge regression to estimate something that looks very much like a Green's function from a simulation with varying SST and fixed pre-industrial forcing, where using 143 years, they can get a pretty nice Green's function at 1 degree resolution. I tried the same thing. So I took CSM2 AMI-PI forcing 145 years, and at first I regridded it to 25 by 25, so I only have 105 points. And then, as any good machine learning scientist does, I just went and imported SK scikit-learn and did a linear regression. And you know, this is what you get. You get something fairly blocky that is maybe vaguely reminiscent of a Green's function. And then I decided to do something silly, which was I regridded this to 1 by 1 to get 63,000 points. And I was curious as to how this would fail, what error it would throw up. And if you just do linear regression from scikit-learn, you get this. And I literally fell out of my chair because this is a Green's function. For all intents and purposes, it has we know this negative sensitivity in the West Pacific, positive response to low clouds in the East Pacific, some kind of dubious response in the Southern Ocean. So it sort of worked despite the OLS condition being extremely violated. So what happens? Why does this work? Why can we infer these kind of Green's functions from these short records? So you're gonna have to bear with me here for 2 slides. If you think of what linear regression is, it's the solution to this problem in case you only have one time series. Say you want to estimate global radiation from global temperature, and you want to estimate this regression coefficient, then the way this estimator ends up being the ratio of the sample standard deviation of radiation to the sample standard deviation of temperature times the correlation between radiation and temperature. Right? This is just a very basic OLS estimator. What scikit-learn does, if you tell it to solve the multiple linear regression problem and to estimate now this vector beta, is it doesn't actually do ordinary least squares. It does something called a more Penrose pseudo-inverse, which, if the OLS condition is satisfied, is the same as the ordinary least squares. But this actually works even if the OLS condition isn't satisfied, and without going into these details, it uses a singular value decomposition. You'll have to trust me on the math, but what this is equivalent to is this. Basically, what you can do is you can build these regression coefficients using the EOFs weighted by the ratio of the variance of radiation by the variance explained by each EOF times the correlation of each principal component with radiation. So it essentially does the same thing, but only using as many principal components as you have available. So the takeaway is that in this case, the regression slopes are the maps, the Green's functions are really built from EOFs. So this is how you can deal with the data sparsity problem, is by building your regression from EOFs. If you want to do regularization or ridge regression, which is what Paolo and Sarah did, it's essentially adding a penalty term to the variance of the different EOFs, such that if you have components with very small variance, they get down-weighted. I can talk to you more offline. This is equivalent to the L2 norm penalty, which ridge regression is usually described at. So you get these Green's functions from not that much data because you're really only using the EOFs and you're really regressing against the principal components. So hopefully that makes sense. Okay, so you can diagnose Green's functions, but do they have skill? What do I mean by that? Well, what I mean by that is, say you take a historical record, the AMI-PI forcing of CSM1, and you do a fit and you get a Green's function, and you get a pretty good match of the GCM over your training interval, which you should. You got 63,000 predictors. But does it have skill in terms of predicting? So then what you can do is you can take an abrupt quadrupling simulation of the same model, convolve this Green's function with a spatially varying SST, and try to predict radiation. And you get, not a great fit, but actually you get about as good of a fit as you do if you use a directly estimated Green's function from a delta function like perturbation. So it has some skill. It's not perfect. You can then say, well, what would the perfect Green's function look like? So you can do that. You can fit both the AMI-PI forcing and the abrupt quadrupling simulation at the same time, and you get a Green's function that is not qualitatively different. But there's enough quantitative differences, especially in the southern ocean, that the historical record doesn't resolve, that it gives you a biased prediction in the future. But at least we know that the pattern, you can get the pattern basically right from 145 years. Okay, so hopefully I've convinced you that you can use this kind of regularized regression and EOF basis to diagnose Green's function from historical and abrupt quadrupling simulation. Can you do it from the satellite record? And the answer is kind of. So if you just use the last 23 years of an AMI-PI forcing simulation, something that's going to resemble series, you get something that resembles a Green's function, but the skill is much, much lower. Basically, you don't really have enough degrees of freedom in 23 years. You don't have a rich enough EOF basis to build a good enough Green's function that's going to help you predict the future. So how do we get around that? Well, one suggestion is to use a Bayesian framework. What does that mean? Well, a third way to look at ridge regression, for example, is a Bayesian way, where you say, okay, I'm going to solve this regression problem of radiation against temperature, but I'm going to put a prior on my betas where I basically would like them to be small with a penalty term. And this, if you do this, you get the posterior mode of this is the same as the ridge regression estimator. But instead of using this prior, what you can do is you can use priors from other models. So here I'm going to use priors from all the other AMI-PI forcing simulations, which, if you're interested, they look like this. They look very similar, actually, to the CSM1 long-term in terms of the pattern. The magnitudes are different. And the reason I do that is because the long integrations of the other models gives me a richer EOF basis on which to build my Green's function. So let's see how this works. So again, we can try to do a ridge regression estimate just based on the last 23 years, which is sort of the pseudo-series simulation, and then try to project it into the future. The nice thing about Bayes is it gives you uncertainty. The posterior mode is exactly the same as the ridge regression, but it has very big uncertainty. And then we can say, well, what if we use a prior from all the other models except CSM2 and just update it with 23 years of data from CSM2? Well, if you do that, you can actually get a pretty good fit, at least within uncertainty, of what the radiative response in CM2 will be like in an abrupt quadrupling simulation. So bringing in information about the spatial structure from other models then does allow you to get a decent estimate using just 23 years of data. That's the gist of the framework, right? So we can diagnose Green's function in models using regularized regression. Do we still need GFMIP? We can do it very fast. But it's very hard to get any kind of decent sensitivity from 20 years of data on its own. But if we do some kind of model data fusion through Bayesian learning, basically we're learning the spatial structure from long GCM simulations, and they all agree it's negative in the West Pacific, it's positive under the low cloud X, it's kind of positive in the Southern Ocean, and then we just update this with observations. So this is sort of the framework that I'm proposing for trying to get observational estimates of these sensitivities from short records. Going forward, well, if you want to apply it to series, you have to deal with the forcing, though this can usually be incorporated easily in hierarchical Bayesian frameworks. We can tweak things, we can include land or sea ice, we can exclude the poles, we can use more simulation, more priors. I don't think this is going to make much of a difference. What I think might make more of a difference is the issue of localization with EOF regression, and two ways I think to get around that are either using Gaussian process regression or using GFMIP as prior. So yes, GFMIP is still useful. I can talk more about this offline. And this should be applicable to a lot of other data sparse problems, like if you want to understand the sensitivity of the Walker circulation to SSTs, or say the sensitivity of precipitation in California to SSTs. Well, let's bring in some structure from the models and then update it with observations. Okay, that's what I have. That's what I'm proposing as a way to try to learn things from observations when it comes to pattern affecting regional sensitivities.
Great. Thanks, Christy. Yeah, if people have questions, just put them in the chat. In the meantime, I was wondering if you could explain again how you use the long. So in your current method, how do you use the long? Like, how do you construct the prior again, basically? That mean in the prior?
So basically, you do this regression, this kind of ridge regression, but in a Bayesian way, for each of the other models. For, like, you know, there's 8 AMPI forcing model. So you do this for 7 models, and for those models, you use both the historical and the future. So you use 295 years of data. So then this gives you a prior on the betas that is trained on abrupt quadrupling simulation. So inherently, the way this is built is it's built from the EOFs from 7 models, right? So that gives you a prior with a lot more spatial structure than you can learn just from 20 years of observations.
Okay, cool. Thanks. Yeah, we're past 1 p.m. Eastern time now. So if people need to head off, they can, but we'll stick around for just a little bit longer to answer some more questions. So Paolo has his hand up. So if you want to unmute yourself, Paolo.
Yeah, hi. Really nice talk, Christy. So I guess one thought I had was, I mean, you proposed some tweaks. One that you didn't mention, but that might make sense, I thought, is if you maybe treat the clouds and the non-cloud part separately. And for clouds, for example, we have information from cloud controlling factor analyses, which you could use as your prior, maybe. And I guess the non-cloud feedbacks are maybe a bit more robust, or I guess most of the differences come from the clouds, right? So yeah, just a thought.
Yeah, I agree. I think that you can, that's kind of the nice thing about the Bayesian framework is you can add, it's a very natural way to add a lot more constraints, especially if they're linear. So yes, I should put that in there.
And then we have another question from Thorsten, which says, did you consider how possible model biases in your prior can affect the result?
Yes, it's if there is a consistent systematic bias in all of the atmospheric responses, then that would lead to a prior that is that is biased, and that bias is going to carry. We're using MEPI forcing SST, so biases in SST patterns won't affect this, but systematic biases in the atmospheric response will. There's no real getting away from that. The nice thing about this, though, is if your observation, even if your model is biased, this is just, you know, a continuous prior. So if your observations would very strongly constrain things to be outside of the model ensemble, the posterior would reflect that if we really had enough observations. And you could look at the difference between the posterior and the prior to see what are the regions where the observations have really added information. So there's a couple of ways to get around that, but ultimately, if there's a systematic bias in all the models and we don't have enough observations, then there's not really going to be any way to get around that.
Cool. Thorsten says thanks. Really cool work. We have more questions than I think we probably have time for. So I think we'll ask Margaret's one, and then perhaps if you have questions, maybe follow up with Christy offline so that we don't keep everyone too long. But so Margaret Duffy asks, does this approach give you an estimate of the SST trend? So I guess, could you back out a SST trend from this? And what does that look like? Is it more like the OBS or more like model projections?
Well, in this case, the SSTs are the predictors. So we sort of give the models the SST trends. So we give that the observed SST trends for the MPI forcing, and then the modeled SST trend for the abrupt quadrupling. So the SSTs are an input to the model. It's an interesting question. So another possible tweak, which is I think what Paolo and Sarah did, they treated the global mean trend separately from the patterned part, which I think is why Paolo and I get slightly different ridge regression estimate for CSM2 for the same model. But here I use the observed SST trends because I was basically curious in trying to do the pseudo series. I was curious if the observed SST pattern has a rich enough EOF structure, because that's really what the observations would eventually be forced with. I don't know if that answers Margaret's question.
I think so. But yeah.
Yeah, thanks.
Okay, you have confirmation. But yeah, great. Thanks again to all of our speakers. So it's a virtual round of applause. And yeah, thanks everyone for coming, and we'll see you next time.
Thanks, everyone.